Okay, so today we're going to start talking about sequences of functions or function sequences. And the first thing we're going to take a look at is what's called the pointwise convergence of a sequence of functions. So by pointwise we mean it's defined for each particular x. All right. So we're going to say that the sequence of functions fn converges pointwise to f, and we denote that with a single arrow. We say that it converges pointwise to f on a set capital A if, when we plug in a value for x and take a limit, the limit of fn of x turns out to be f of x for every point in A, for all x in A. So if that happens, then we have what's called the pointwise convergence of the function sequence. Now, one thing to note is that when we plug in a value for x, this sequence fn of x is just a sequence in our usual sense, right? So the idea of the limit as n goes to infinity of fn of x, that is something we've defined already. So this is not really a new definition. We're just applying our definition of convergence of sequences to every point in a set A. All right, so we're going to take a look at finding the pointwise limit of a function sequence with our first example. And that's going to be each member of the function sequence fn is equal to x to the n. I should probably make that x explicit here so that fn of x equals x to the n. All right, so that's our sequence of functions. F sub 1 would just be x. F sub 2 would be x squared. F sub 3 would be x cubed, and so on. And we're asked to find what this sequence of functions converges to on the interval 0 to 1. So the first thing I'm going to do is graph a few of them to see if we can get an idea of what's happening. So as I mentioned, if n is 1, then we get fn of x equals x. And that's just the straight line. So here's n equals 1. If n was 2, then f sub 2 of x would be x squared. So that would look something like this on the interval. N equals 3 would be x cubed. So that would look something like this. And so what we see happening is as n increases, this curve becomes more and more pronounced until finally it looks almost vertical, right? That's not a great curve at the end. It looks almost vertical when you get near 1, but everything else is flattening out at 0. So let's think about what this function sequence does in the limit. All right, so let's note that first off, if x is equal to 1, notice all of the functions meet at the point 1, 1, because 1 raised to any power is 1. So if x is 1, then fn of x, I'll say fn of 1 is equal to 1 to the n, and that just goes to 1. Right? It's the constant function 1, but it converges to 1. Now, what happens if x is anything else in the interval? Well, if x is anything else in the interval, it's smaller than 1, so it's some fraction between 0 and 1. And if that's the case, well, I should be a little careful, not necessarily a rational number, but thinking of it as just a fraction smaller than 1. If that's the case, raising it to higher and higher powers drives it to 0. Right? So if we had something like a half, then you'd get a half, a fourth, an eighth, a 16th, a 32nd, a 64th, and it would go to 0. Even if we have something really close to 1 like 0.99, if you raise 0.99 to a high enough power, it goes to 0 as well. So what we're saying is that for any other point in the interval, x to the n goes to 0. And what that does is define our limit function, f of x. We have to define it piecewise. It's equal to 0 for every x that isn't 1, and then it's equal to 1 when x is 1. So what that looks like, let me get a color that I haven't used yet, is the constant function 0 until we get to 1, and then it just jumps up to the point 1. Now, this is in some ways kind of an unfortunate example for us, because if you think about what has just happened, we have a sequence of functions that are all continuous on 0, 1. And the sequence of functions converges everywhere to this function f, but the limit function f isn't continuous on 0, 1. Right? And that's something that we really would like to have happen, right? We would like for sequences of continuous functions to have continuous limits. And so this example shows us that pointwise convergence is not enough for that. So we're just going to note f is not continuous even though all of the other functions are. So this is kind of pointing out a need for something that's a little stronger than pointwise convergence. So we're going to define next a notion of uniform convergence, which is stronger than pointwise, and which has the really nice feature that if you have a sequence of continuous functions and they converge uniformly to another, then the resulting function has to be continuous. So that's next.